Today we are going to do section 5.5. First, let's look at the book. Let's see. Okay, let's focus on that. Actually, we mostly have to focus on this, right? And yeah, that's good enough. Okay, next, page 166 and 167. Let's see. Let's come in a little better. My camera is not focusing. Why is that? Okay, there we go. I think it finally decided to focus. All right, and then a little closer on top. And a little bit closer on the bottom. All right. Next, 168 to 169. We have, let's see, first let's look at the whole page. Let's see. That should be it. And then a little bit zoomed in on top. It looks, and then a bit on the bottom. Let's see, maybe I'm tilting the wrong direction. Okay, that looks a bit better. Maybe do the whole page again. That way it's, I don't know. All right, that should be good enough. And finally, 171 and 172. We have this thing, okay, that looks somewhat okay. All right, and then a little closer on the top. And a little closer on the bottom. Okay, that should be it. So today we are going to do section 5.5 on page 165. Now this is, we're going to do something about mass and moment of inertia, okay? That if you had physics, then you might remember it. Or if you haven't had physics, then you sort of know what it is anyway. So mass is, please read the first two paragraphs on the page 165. Okay, so some introduction of what we mean by mass. And continuing, we have, please also read this part yourself, okay? Just the description and definition of mass. In fact, please finish this thing all the way to this part. Because and not much is happening here. Because we're talking about mass and density distribution that I'm going to go over it slightly, but I'm not going to talk too much about it. And I feel that you're faster if you just read this yourself, because there's not much math going on here. So what happens is, let's say you have some kind of a curve, right? So if you have a curve, then you can parametrically express it as x equal to x of s and y equal to y of s. And at those points, you might have some kind of a mass at each point. Then if that is the case, then we can define it this way. A particle of mass m at the point S of the curve L we'll name it S comma m. That is, so at location S, the mass is equal to m. Okay, and then next, the distribution mass on the curve is a function ms. Okay, the distribution mass, if we go along the curve L, then ms at 0 is 0, because there's nothing there. And then as ms go on, it's an increasing function, or at least not decreasing. Okay, and that is because as it goes on, you're adding up everything along. Okay, so your wire is going longer, and therefore it has more mass. And so next we have, and then the mass of a segment is calculated as the endpoint mb and minus ma. And then sometimes, of course, you can have a line that actually has nothing but a bunch of bunch of stuff there, that is a bunch of particles. So you only have mass at certain locations, okay, and finite locations. In that case, then your mass will be defined as, your mass is the same until you reach the next chunk of stuff, particle, then it jumps to M1, and then it continues to add, jump to M2, and so on, until you add up all your particles. If you have a finite number of particles on your finite length of a wire, so then the rest of the wire has no weight, okay? So that in that case, then your ms is a step function. So the mass goes, go up and stuff. So then, and at any point, the mass is going to be as defined as before, the later location subtracted by the before location. So if you want to calculate a chunk of it, how much mass there is, then you just do subtraction on this thing. And then if a distribution of mass is continuous, we take that to mean that ms belongs to C1. That is, its derivative is continuous as well. And then the density is defined as m prime, that is the derivative of s. The reason is because normally density along a wire anyway is defined the same as the derivative. Okay, this is is your difference in mass divided by the difference in length, and that gives you the density of that wire of yours. And then so next we have the total mass, then you just add it up, and if it's a continuous function, then you take the integral. So then here's the total, right? So the total mass of a certain chunk, then you take the derivative of m prime ds. An arbitrary distribution, you can also write it like this, okay? The dms, being a dms is m prime s ds. So that's how that works. So please read all this stuff yourself, okay? And read any details that I might have missed. And so now let's look at section 5.2. So next, let's look at section 5.2 on page 167, and that's talking about the moment of inertia. Well, there is not much to say here either. That's really math. So please read this yourself, okay? This entire, this thing here, as well as the following page. That is, that tells you what moment of inertia is and how to calculate it, which there isn't much to it really. Okay, the following page here, and which come to example A at the bottom. Okay, which give you a very simple example that doesn't take much. So please go over example A yourself and make sure the math comes out and some quick addition or multiplication or something, and the same as example B. All right, and if you just read it, it's just the basic calculation of density that's done in similar to what is done in physics 101, basically, or whatever. But I will talk about it a little bit, okay? But I'm not so sure that you really need me to talk about it. So the moment of inertia is defined as the mr squared, and add it all up. What m is the mass, okay, and then r is the distance to the axis that you're referring to. So moment of inertia always have some axis. So the mass of an object compared to the distance. Let's say you have an object here and there's your axis, okay, so it has a distance here. So m times the distance squared, r squared, is your moment of inertia. And if you have a bunch of stuff, right, then all their moments of inertia add up. That's all there is to it. So let's look at the properties, okay? The first, if a total mass is divided into several chunks, then the moment of inertia is calculated as the sum of the inertia of each one. And so that's property A. Then property B, if you have more mass to your chunk, then your moment of inertia increases. Property C, if mass is moved farther away from your axis, so you take your pile of stuff and you move it away from, say, this is your axis, okay, then your moment of inertia increases. Well, that's because your moment of inertia is defined as mass times distance squared, right? So obviously, the farther you move away from your axis, the distance bigger, your Im is also bigger. And so that is that. Now, so the next part here at the bottom is we're going to find the moment of inertia about the x-axis. Now, pay attention to that, okay? The rest of this paragraph is about calculating stuff against the distance about the x-axis. Now, if you miss that part, then it wouldn't make any sense. You wouldn't know what you're doing. So let's look at the next page. Page 168, where we do, then we define certain things like being that we're calculating the moment of inertia against the x-axis, the horizontal line, then we need to calculate y distances of your stuff, right? And then, so then the moment of inertia will end up being the mass times, the difference of the mass times the distance, the y, okay, and then times your mass basically is what this is. And in the, so please read this yourself. Basically, if things are continuous, then eventually the moment of inertia, this is about the x-axis, very important, okay, is going to be integral of the y squared times dm. This and that comes from taking this definition to infinity. When the limit of this goes to infinity, that would give out this result. So please read that yourself, okay, and work out some of the details that I am not going to talk about too much. So next, let's look at example A, which is a simple example that has we have two things. One, some continuous wire, and then you have two chunks of stuff together to make your entire collection of stuff. So, and then to calculate moment inertia in that case, then you have two situations. One is the continuous situation for which you do integral. The other one is the individual situation where the ms2 is just is a step function of 2 units. Okay, it has 2 steps. So when you integrate, you're basically calculating two things. Okay, you're not really integrating. It's not much of an integral when you do step function. So you just plug stuff in and make sure this thing comes out. Okay, and I have some notes written here that should help you do calculations, although I'm not sure why you need help for this. It's all fairly straightforward. And so next, look at page 169, example B, where we have what is that? Oh, a plane. So now instead of stuff on a wire, now stuff is in a plane. Well, that changes nothing. Okay, basically you calculate your mass and then you calculate your distance, but this time it is you're calculating the moment again about the y-axis. Now that's very important. So then the x is being squared. See the x is being squared here, and then you sum it up, and your moment end up being x squared times the mass and stuff. Okay, and the sum becomes an integral if things are continuous. And so please, again, read this yourself. And with that, we have come to the end of this section. For the most part, just, spend a little time and go through it carefully and make sure everything comes out. And with that, we will get to the homework. Let me write it down. So for homework, please do problems on page, 169. Please do problems 1, 2, 4, and 5, 6, 7. And that should be good enough. Okay? And we are done. I will talk about them. Okay, so let's look at problem 1 on page 160. Give me a second here. So problem 1 on page 169. Okay, not much happening here, really. We have x is cosine, y is sine, and m prime is this a slap on the Pythagoras theorem, okay, of the distance of something. And then the total mass is the integral, which if you integrate this thing and then figure out how it's done, where well, anyway, I used the integral calculator, and then that is gonna come out with this equation right here. Okay, I mean this thing here, which is correct. So that's that. That's problem 1. Problem 2 is a similar thing, but now you're gonna go along the curve of the thing. So ML, starting as degree equals 0, gets more and more. Okay, and as it goes past pi, it continues to increase because you're imagining the the curve starting at 1, 0, and then just keep increasing and winding all the way back. By the time you get back, you got an entire wire, okay, that you could straighten out to be the length of whatever, pi or 2 pi or something. So that's how ML is defined. So then with that information, then you have to be careful so that you don't get confused at what's going on. Now ML at first is easy enough, right? The m prime of s, the density is just s, which ML is the integral of s, which is s squared over 2 from 0 to 2 pi. That's fine. However, from pi to 2 pi, m prime of s now is equal to 2 pi minus s. Okay, this is important. And once you know that, in other words, m prime of s looks something like this. And then, so as a result of that, from that part on, ML is going to be equal to pi squared over 2, because ML is being measured from 0. Okay, so you start out having this part. So this has to be added, and then you'll do your integral, which end up being this particular equation with well, I put it in the calculator, so I had to use x. So well, x here is the same as s, okay, and that is the right answer at the back of the book. And so, well, okay, there's not much worth mentioning here. And then, so next, let's look at problem 4. We need a moment of inertia about the what, y-axis. Well, that's simple enough. You just slap x squared in there, and then you're done. Okay, and then so let's look at problem 5, which well, problem 4 doesn't have the answer at the back of the book, but problem 5 asks you to use problem 4, okay, to be able to come up with the answer. So problem 5 does have the answer. So if you get this right using this, then that must be right as well. So problem 5. We're redoing example A, but this time we're doing it about a y-axis. In the book, the example A was done about the x-axis, or something like that. Yeah, I think so. So anyway, well, then we just plug stuff in. Okay, just like example A, here's what is that? About the y-axis, so this is the x value or something, whatever. The point is you plug in the right things, right? And then you have a bunch of tiny integrations to do. Plus the second part is discrete, or you're integrating against the step function or whatever. The point is then you add up these values, and then I got 2/3, which is correct. So that's good. And yeah, so this anyway, so just go ahead and do that, and then we're good. And then so this problem 6, then we need to calculate some basic principles. So problem 6 answer, I have it in one line. Okay, well, it's just the distance squared, right, and times dms, and then that is going to be your moment of inertia, right, r squared times m. So then problem 7, we're demonstrating problem 6. So let's plug this stuff in. Okay, this is xs squared, ys squared for the continuous part. And then these are the discrete parts, and then we come up with some kind of an answer, and that is correct. And that's about all I have to say about this section. Okay, and that's so that makes a very short, quick section.